Good morning, everyone. My name is Patrick Alexander. I'm from Columbia University, and part of this project, our group is studying the contribution of the cryosphere. So the changes in the Arctic, how are they affecting the ocean? And our role is to just quantify how much ice is being lost and how much fresh water is going into the Arctic Ocean. And so these are kind of the areas of ice in the Arctic. So there's the Greenland ice sheet in the center there, which is about a third of the size of the US, and it's about 2 miles thick at its thickest. So it's a very large mass of ice. And then we also have sea ice in the Arctic Ocean, and all of that is changing. So we want to know how much it's changing and where the water is going to the ocean, and sort of the timing of that, so that we can better predict how the ocean is going to change. So why does this matter? So we have observations from satellite measurements that show that ice is being lost from the Arctic. So on the upper right, there is the Greenland ice sheet, and that's a measurement from the GRACE satellites that are measuring gravity, and it's showing that the ice is decreasing over time, and it also, you can see where it's going into the ocean. And then the sea ice in the Arctic, you can also see from different set of satellites that that's also decreasing over time. The total amount of water from the Greenland ice sheet, for context, that's about half of the Gulf of Maine in that time period there. I think if you combine the other sources, it's probably one Gulf of Maine. So that's kind of a lot of water going there. And so we want to know what's going on in the ocean. So that's kind of the next link in the chain of this project, which Xiaobiao will be talking about. So our role is to gather the historical data. So there's a combination of models that are constrained by observations and actual observations of how the ice is changing. And so we're combining kind of liquid water, the solid ice, and the sea ice changes, and looking at the historical period, and then the model projections for the future. How is that going to change? How's that going to change the ocean? And then we'll see all the links down the chain for the next. So now we'll move on to Xiaobiao, who is online.
So my name is Xiaobiao. I'm from FSU. My contribution to this project is physical oceanography, mostly ocean modeling. So under this new Arctic framework, the most obvious or most striking phenomenon happening in Arctic is the sea ice is melting in line with the warming observed in the rest of the global ocean. So as a physical oceanographer, the number one question we have is how is this existing change or variability is represented in the global ocean models? And secondary, how well the Arctic or global ocean changes in the coming decades. So here what I show is the declining of the sea ice in the Arctic Ocean. The black line is annual averaged sea ice extent observed and presented by the NSIDC, and the red line is the equivalent of that in the global simulation. So as you can see, the sea ice is declining, but is not like a uniform or constant rate. So it declines very fast in the 90s or early 2000s, but kind of like slower in the recent past 10 years or so. So as you can see, the model actually can represent this evolution quite well, including interannual variabilities. Next slide, please. And significant changes also takes place on a much regional scale, such as the Gulf of Maine. So where the health of ecosystem can be significantly impacted by the changes of water properties. So here, what I show is from the same global 120-degree HICAN simulation, the sea surface temperature variability in the Gulf of Maine. The red is the model, and the black and the gray is two observational products. One is OISST that has a 1/4 degree, but the data starts in the early 1980s, while the other one had SST has a coarser resolution but extends further to the earlier years. So as you can see also, the temperature change in the Gulf of Maine is not linear or in constant pace. Actually, it went through a few periods, like from 70s to all the way to early 2000 was kind of stable, relatively speaking, increased very fast after 2005. And as Demian mentioned earlier, in the very recent, in 2004 of 2024 or 2025, it experienced some sort of cooling in the latest. So the model, we show that it can represent some of these variability quite well. So then the question is, what drive these the variabilities, and also how the change will continue or will change in the coming futures. Next slide. So connect to the future and other teams. So we performed the basin scale, downscale projection simulations using the atmospheric anomalies from the SIMI 6 climate scenario 7.0. This is a 50-year projection. We are planning to perform different projection using the global configuration, because we see the global model has this potential to represent some of these features really well. So the model output will be used by other teams of this project, such as phytoplankton or zooplankton and ecosystem modeling, etc. Thank you very much for the attention.
Okay, fantastic. Yeah, I'm calling in from New York, and I'm at Columbia University. In the interest of full disclosure, I got my hands wet in oceanography in the Gulf of Maine, working with Barney Balch. And my interest in this region has remained even after I moved to Columbia University. So in 2016, when the network paper came out that Damien spoke about, I had a student working with me on looking at how the freshening of the Arctic region was, the melt of sea ice was affecting the North Atlantic Ocean. And one of the most astounding things that we saw then was that the Western North Atlantic gyre was spinning faster. And this was because of accumulation, a lot of fresh water that was making those waters buoyant. And what we noticed is what Damien showed, that the Labrador current was slightly changing in that the arm that moved eastwards was strengthening, and the shelf slope waters were weakening. And this is when I reached out to Rick Wally, who I want to give a shout out to, and asked him whether this would be something that we could tie with to explore the effects on the lobster industry. And that is what led to the development of this NNA project. So what I'm going to be talking about is the data that I've used over here comes mostly from the Department of Fisheries and Oceanography in Canada, and I'm really grateful to them for making their data accessible. and also to many of the agencies, state agencies along the U.S. East Coast, as well as the data from the NOAA's ECOMON program. So this is real data that we were looking at. We had spent some months compiling all this data, and what I will try and show you is that that this information that we are getting is showing, at least till the year 2022, is that the nutrients that we are receiving in the Gulf of Maine, and this is focusing mostly on the Gulf of Maine. I've got data from other areas from the Maritime Canada region down south, but this is focusing on the Gulf of Maine, where the shelf slope waters have a huge impact on the nutrients that come into the Gulf of Maine. And here we can see the major nutrients that support phytoplankton spring blooms in the Gulf of Maine are decreasing, at least till 2022. I'm really happy to see that there is an upturn and that we are getting more colder water coming into the Gulf of Maine. So that should make a difference after 2023. Can I have the next slide? So we are seeing a decrease in nutrients. And this, what I haven't shown is that this is related to the amount of warm water that we see coming into the Gulf of Maine. So it is really clear that there is more Gulf Stream water coming into the Gulf of Maine, and this can be seen in the trends in the salinity and the sea surface temperatures and the bottom sea water temperatures as well. But what this does is that it has had a huge impact on the spring phytoplankton bloom. And it's not seen so much in autumn or in summer or in winter, but what we see the onset, this decline in nutrients is having an impact on phytoplankton blooms in the Gulf of Maine. Can I have the next slide, please? And this projecting only the keystone species Calanus finmarchicus over here, and you do see that during autumn, the impacts of this decline in phytoplankton blooms is having on Calanus up to about 2021 till when we have this data. We have seen a decline, so in both autumn as well as in winter and summer, and to some extent also in spring. So this keystone species, we see this trend also in some other zooplankton species that support the lobster larvae, and this is what will be spoken by the eco. This will be spoken by in the population dynamics part. Thank you.
I'm Jaehong and working with Dr. Stoll at FSU. We developed the zooplankton distribution model in the Northwest Atlantic area, especially focusing on the Calanus marchicus that grazes on the phytoplankton and serves as a main prey for lobster larvae in the Gulf of Maine. So the main goal of our projects is to find out how rapid Arctic change could affect the survival of the lobster larvae in the Northwestern Atlantic, including the Gulf of Maine. To do this, we have two main research questions. First, how will changes in the structure of the ocean circulation affect the primary and secondary production? Second, how will these changes in the primary and secondary production affect Calanus marchicus and its link to the lobster larvae? Next slide, please. So let's talk about why we study Calanus marchicus first. Calanus marchicus is one of the copepod species existing in the cold water and is one of the central species in the North Atlantic food web. It mainly contributes the mesozooplankton biomass in the area so that it is a dominant grazer of the phytoplankton and heterotrophic protists. And its high lipid content makes Calanus marchicus an important prey for many species. Therefore, studying the impact of the climate change of the Calanus marchicus is important to estimate the lobster larvae survival rate change. because climate change will alter the colonist market's distribution and phenology, which will directly affect the prey availability of the lobster larvae. Next slide, please. So what we are doing is developing the physical and biochemical coupled model. For the physical model, we'll run the offline model, which requires pre-calculated velocities, temperature, and salinity, and Xiaobiao provided those estimates. Then we will couple the physical model to the biochemical model, and we are planning to use Joaquim's observational data for the model validation. On top of the coupled model, we'll build up the colonist Mersch's habitat model, and when our modeling is finished, we'll pass our daily and monthly colonist Mersch's concentration data outside of the Gulf of Maine to Andrew, who studies the ecosystem model. Thanks.
What we've heard coming up to now has been a lot of ecosystem processes affecting bottom-up things in the ecosystem and how that might shape what we see for American lobster larvae and the production of, or self-production of the population. And what we're really interested in is what happens when there's a change in the status quo, which we very clearly outlined here. So what we're interested in doing is figuring out how changing oceanography affects patterns of reproductive lobster behavior and how all those things manifest to changing larval supply. If we can get a understanding of how larval supply is changing, maybe that can give us that predictive tool to understand how these ecosystem processes affect the earliest and most vulnerable subset of the lobster population and what that means to the population as a whole. In order to do that, we have developed a Lagrangian particle tracking framework for American lobster. And we've been using a combination of information sources from state level, federal level to try to understand the distribution of females and how their changes of behavior and distribution are affecting the larval supply and how we can relate that to trophic dynamics, predict what settlement might look like, and then what settlement translates into the future. In order to do that, we're taking the HICOM and the Murrow products, as briefly mentioned earlier, that simulate the physical environment as well as the trophic environment, and then relating that to patterns of larval abundance, and then using that to tune what we think settlement might look like, as well as changes in the thermal environment, how all those things come together to affect this critical subset of the population. One of those data sets that we've been looking at has been the trawl survey data from the state and federal levels. And if you were to look at the distribution of the potential spawners within the Gulf of Maine over time and over space, we see that there are substantial changes. In concert with the changes in landings, we've seen a parallel change in the distribution and abundance of potential spawners, where we had a peak in abundance back in 2016, similar with landings. And over the course of 2001 till now, the distribution of those females has also been shifting farther and farther offshore. So we're trying to figure out how does that shift impact patterns of larval connectivity and larval supply. And to briefly summarize what I'll go over later at 11:35, the distribution of females is predominantly affecting the patterns of larval supply, where we're getting a shift of females offshore, and the changing distribution and abundance is affecting the amount of larvae that we're seeing. In southwest regions, we're seeing that there's been an increased supply of post-larval lobster. In northeastern regions, we've seen that the patterns of larval supply have actually been decreasing, and that these patterns mirror very well the distribution and abundance that we're seeing of females that are in those locations. So it's a means of saying that if we can integrate all of these ecosystem and population dynamics and these surveys together, we can hopefully get a bigger picture of what's happening to this critical subset of the population. And then we can pass it off to people like Miguel, who then take that, put it into population dynamic models, and really understand what the large magnitude impacts are from the change.
My name is Miguel Barajas. I work with Kathy Mills on the population dynamics component of the project. So our work is kind of really looking into the past research around recruitment and abundance of lobster and how that has been tracking with ocean temperatures. And we're using that as a foundation to then simulate population dynamics forward into the future under these scenarios of ocean warming in the Northwest Atlantic. So we have 4 main questions that we're kind of looking into. So I'll go over them briefly. So at a large level, we're looking at how do Arctic changes affect the distribution, abundance, and productivity of lobster? And then second, how do these temperature shifts link mechanistically to growth processes, reproduction, and improvement dynamics? And then third, what do we expect these regional differences in lobster population responses across the US and Canada? And then lastly, how do these biological changes interact with fishery behavior? So, obvious statement here, but we all know lobster is a super valuable fishery. And what happens to the lobster fishery, the changes have major consequences socially and economically. And so it's really important to better understand these interactions, across temperature, growth, productivity, disease, and harvest. And by better understanding these interactions, our hope is that we can identify some early warning signs. So, things that managers, communities can use to adapt as things change in the future. So ultimately, the goal here is to build a framework so we can anticipate future change and just really help the communities support that. So the population dynamics piece really serves as a bridge between the ocean modeling and the environment, the biology of lobster, and then the humans dimension side of the system. So we'll be taking the ocean temperature estimates, feeding them directly into the population model, and it'll drive biological mechanisms of growth, maturity, reproduction. We'll also be taking in the larval lobster modeling trajectories that really integrate, the base of the food web, and that'll kind of support, the capacity of the population dynamics. And from there, the population outcomes of the lobster model will then form a feedback loop with the bioeconomic modeling and with the social indicator. So from there, we have this two-way interaction where population outcomes directly feed into fishery behavior and vice versa. So thank you, and then I'll pass this on.
Miguel. Hi, folks. I'm Jay, and I've been tasked with the overwhelming challenge of figuring out what's going to happen to the fishery. And we're doing that through a bioeconomic modeling perspective. And we asked the question of how do you connect ecosystem dynamics with human activities? From a pure economic standpoint, that is trying to figure out what is production in the fishery. How do fishers actually catch the lobsters that they're producing for the seafood market? Essentially, we want to figure out what is fishing effort and therefore what is fishing behavior. Fishers are dynamic actors in a coupled human-animal system. If you're familiar at all with any sort of fishing, you recognize that humans don't just respond to what's happening to the number of fish. They respond to a numerous number of things, including the weather, but also the government, markets. They think about political and school systems. There are so many other things that impacts how a fisher makes decisions about fishing effort. And how those decisions scale up ends up being what we think of fishing effort in stock assessment or other fishery management. And so we try to figure out how fishers use their resources and make decisions with the resources that they have to make lobsters or catch lobsters. It's much more about the numerator side of Amy's analogy. How we're doing that is, well, we say bioeconomic modeling. Really does a two-part process where Miguel and other brilliant people are giving me an idea of how many lobsters there might be in the water to catch. In order to actually understand how the fishery responds to that number, we need to really have an understanding of fishing effort. How we look at that is through looking at decision-making processes and using mental models to sort of characterize fishing effort in the lobster fishery. That feeds information into how we build an agent-based model representing the fishery, in which hopefully afterwards we have feedback cycle of fishing mortality or landings that feeds back into the population dynamics model. And from there, we can also gather information about what does the fleet dynamics look like after a number of years? How does it change? What are the business strategies? And how does fishing effort shift across multiple scenarios and landscapes?
Josh Stoll, faculty in the School of Marine Sciences. I've been working with a really fantastic team over the last couple of years on this. Our work focuses on the human dimensions of the fisheries. Obviously, the lobster fishery is the most valuable fishery in the region and one of the most valuable fisheries in the world. But as this group has been talking about, there's been a lot of change. That change is not just happening in the water, but also within harvesters themselves. As evident by this figure on the right, this is an illustration of number of traps fished in Maine by licensed class. And you can see this really incredible shift from LC2s, which are sort of a smaller vessel, to LC3s. So you see these sort of socioeconomic change that's happening. And despite all that change and all the monitoring we do of the biological system, I like to think about our biological monitoring of lobster as kind of the Cadillac of monitoring. We have a bit of a blind spot or monitoring gap of the human dimension. And so that's really where our really around this idea of how do we develop a set of sentinel indicators of resilience that understand how the fishing fleet is doing so that fishing industry, coastal communities, and policymakers have that information to make decisions around. If you want to do a deep dive into this work, we have a couple of presentations in the community session, which is 3A at 11:35. So what does that mean? We, through a set of work that we won't go into too deeply here, we developed a set of these 8 indicators. So you can't go out and measure resilience. So instead, it's a latent construct. So we went out and asked people, what do we know about resilience? How do we know something is resilient? And we ended up identifying a suite of 8 indicators that underscore resilience in the fishing fleet, from everything from direct things like risk taking to things like related to income and occupational health, to kind of external drivers like coastal accessibility. Over on the right, you can see some of what that data looks like. We assemble a suite of indices to put into these indicators, and I've been working on developing those for the last couple of years. And now through this work and through additional funding from the National Sea Grant ALI program, I've been working to help integrate these data into the stock assessment process. So a huge shout out to Captain Reardon, Tracy Pugh, and others who worked tirelessly with us to help us understand the stock assessment process and think about how do we integrate these socioeconomic data into our understanding of the system. And then to complement that, we're also building out our capacity to take these data sets and work with communities to say, how do we actually use this data to inform decision at the community level, and building out our capacity to take this data and downside with the question that how. So that's sort of in a nutshell what our fishing indicator work is about. I'll end with this observation and then hand it back to Damien. When I started as a faculty member here in the School of Marine Sciences, and I looked around at all the work, the incredible work that's being done in the lobster fishery. I really had data, and a lot of people had been doing it for decades. And there's this incredible amount of biological and ecological data around lobster fishery. And I looked at it and said, wow, that's crazy. And they pretty early on made a commitment to our team to say, let's try to work on that and try to build out that capacity through time. So this is, we're talking about a single project here, but my vision is this is a long-term process. And the way we get to that is through collaboration with people like everyone who's at the table here, but hopefully all of you as well. So excited about finding ways to make this not just a kind of a project to be done with, but part of an ongoing monitoring of the system, because we're serious about sustainability of the fleet and the fishery. We can't just think about the biological and ecological, we also need to think about this as good. So this is a call for collaboration. It's clearly this event. So thanks so much. And hand it back to Damien or whoever takes the baton.